Welcome to Ask and Learn.
We're asked to prove that a of m plus 1n is greater than or equal to a of mn whenever m and n are non-negative integers, where a is the Ackermann function. Recall that the Ackermann function a of mn is defined to be 2n when m is equal to 0, 0 when m is greater than or equal to 1 and n is equal to 0, 2 when m is greater than or equal to 1 and n is equal to 1, and a of m minus 1, a of m n minus 1, when m is greater than or equal to 1 and n is greater than or equal to 2. So to prove this statement, first let Pm be the statement a of m plus 1 n is greater than or equal to a of m n for all non-negative integers n. In fact, we can make this a strict inequality. I don't know why they made it that way in the problem statement, but yeah, for all n greater than or equal to 0. So we'll use induction to prove this. So for the basis, we have, well, I suppose first, let's consider n is equal to 0. Then we have, no matter what m is, a of m plus 1 n, well, m plus 1 has to be greater than or equal to 1, and so it follows that this is going to be, n is 0, maybe it is greater than or equal to, okay. This is greater than or equal to then. This is going to be a of m plus 1, 0, which is equal to 0, which is equal to, and then we have, depending on what m is, a of m 0 is going to be 2 times 0, which is equal to 0, if m is equal to 0, and 0 if m is greater than or equal to 1. As we see that in either case, it's going to be 0 for all m. And so we've shown that a of m plus 1, 0 is greater than or equal to a of m 0. In fact, they're equal. And so we've proven that part. Now, from here on out, we're just going to consider n greater than or equal to 1. The rest of the entire proof. Now, for the base case, we have that, suppose that m is equal to 0. Well, we have a of 0 plus 1, which is 1, and then n. We have it from a previous exercise. This is 2 to the n. And we have that a of 0 n, since m is 0, this is simply going to be 2 times n. And we know for a fact that 2 to the n is greater than or equal to 2 times n, which is a of 0 n. So it follows that P0 is true. Now let's consider when m equals 1. We have that a of 1 plus 1 is 2, n, and this is by the recursive definition a of 1, a of 1, and minus 1. And recall from a previous problem, we have that this is the same as 2 to the a of 1 n minus 1. My mistake, this should be a of 1, a of 2 n minus 1. And instead of writing it like this, I think I'm going to write it out more explicitly. So this is equal to a of 1, a of, again, a of 1, a of 2 n minus 2, and we can just keep chipping away at that last term until eventually it becomes a of 1, a of, and then we get 1, 1, and this is equal to 2 to the 2 to the, and so on, all the way up to 2 to the 2. And clearly, since we have raised to an exponent n times, that even if we just raise to 1, we still have that. So we have that a of 1n from the previous problem was 2 to the n. And so we have that a of 2n is going to be strictly greater than 2 to the n, which is equal to a of 1n. So it follows that statement P1 is also true. For the inductive step, let's suppose that the statement Pk is true for some k greater than or equal to 1. So we're starting at that part of the basis case. In other words, we have that a of k plus 1 n is going to be greater than or equal to a of k n for all n greater than or equal to 0. And again, we're really only considering in this point, you already proved for n equals 0, so we're just considering when n equals 1 or greater. We want to prove that p of k plus 1 is true. So again, let n be greater than or equal to 1 in this case. We have that a of k plus 2, k1 plus 1, n, well, this is going to be a of k plus 1, a of k plus 2, n minus 1. You see here that we're kind of stuck. That's one way of looking at it. Maybe the best way to prove this might be to use essentially another level of induction. So we have that pk is true, but we have that we know that a of k plus 1, 0 is greater than or equal to a of k 0. We already proved this. And let's make another supposition. So we're going to suppose that a of k plus 1 L is going to be greater than or equal to a of k. I'm sorry. We're proving for the case when this is k plus 2 and this is k plus 1. So we know this is true. And we're going to suppose that a of k plus 2L is greater than or equal to a of k plus 1L for some L such that L is going to lie between 0 and n minus 1. We need to prove that's true for n, so I'll leave that off. Then we have that a of k plus 2 L plus 1 is equal to a of, and this is going to be L plus 1 is greater than or equal to 2. This reduces greater than or equal to 1. So if L is equal to 1 or 0, this is a of k plus 2, 1, which we know if n is equal to 0 is going to be 0. And actually, in the case that n is equal to 1, this will be 2. And if L is greater than or equal to 1, if L plus 1 is greater than or equal to 2, so this is going to be a of k plus 1, a of k plus 2, L. So first of these is 2, and second of these, a of k plus 1, a of k plus 2, L. I'll recall that by our inductive hypothesis, this is going to be greater than or equal to a of k plus 1, a of k plus 1, L, which is equal to a of, this is going to be also have that this is if L is greater than or equal to 1. And now if L is equal to 0, we have that the right-hand side A of k plus 1 L is going to be 0. So we have that if L is equal to 0, then A of k plus 2 L is greater than or equal to A of k plus 1 L, since they're both 0. And of course, that is greater than or equal to 1. We have A of k plus L 1 L. This kind of depends. So if, well, we know k plus 1 is going to be greater than or equal to 2. And we know that L in this case is greater than or equal to 1. So we have that this could be A of k plus 1, A of, and then if L is equal to, say, 1, and this just becomes 2, and clearly this is greater than A of k plus 1 L, and on the other hand we have that L is greater than or equal to 2. Well, this becomes another thing. It's certainly going to be greater than or equal to A of k plus 1 L. So yeah. So we've shown that A of k plus 2 L is greater than or equal to A of k plus 1 L for 0 less than or equal to L less than or equal to N. I don't know what other way to do this, but we have that A of k plus 2 N is by the recursive definition A of k plus 1, A of k plus 2, and minus 1. And since we assumed A of k plus 2 and minus 1 is, well, this is going to be greater than, under the hypothesis, A of k plus 2 and minus 1. And this is going to be greater than by our second proof by induction, and in fact the second inductive hypothesis really, A of k, A of k plus 1, n minus 1. In this case we're assuming that n minus 1 in the statement is true, which is valid since we know that it's true for 0. So we're just using induction. And we have that this is the same as A of k plus 1 n. This is what we wanted to show. So it follows that g of k plus 1 is also true, and therefore, by the principle of mathematical induction, it follows that A of m plus 1 n is greater than or equal to A of m n for all positive integers m, and for all positive integers